Hello, welcome to next session. In this session, we will solve way 2012 XC solid mechanics paper. Okay, here question 1 to question 9 carry 1 mark. Okay, the axial force diagram for the weightless beam subjected to inclined force P is equal to 5 kilonewton is this is the diagram, and here A and C are the support. A is the rigid support and C is the roller support. Okay, and this tangent is given by 3 by 4. Okay, 5 kilometers load is given. Okay, now to find out the axial force, that will be 5 cos theta. Okay, sorry, 5. If the angle is angle theta, then it will be 5 sin theta. Okay, so the horizontal and vertical reaction will be provided by the rigid support. Suppose RAH is the horizontal reaction. Okay, so RAH is equal to 5 sin theta is equal to that 5 sin theta. Okay, so RAH will be the horizontal component of this. Okay, so that will be 5 sin theta, and sin theta is your 3 by 5. So RAH is 3 kilometer. Answer is A, because RAH, sorry, axial force becomes 0 at B, and it is at 3 kilometer and becomes 0. Okay, next, a block of weight W connected to two springs with spring constant K1 and K2 rest initially on a horizontal frictional surface. Coefficient of static friction between the block and the surface is mu. Both springs are initially undeformed. The magnitude of force F applied to the second spring is now gradually increased. The block will start to slide when F becomes option A mu W, option B K mu W divided by K1 plus K2, option C K2 mu W divided by K1 plus K2, option D K2 mu W divided by K1. Okay. Now, when the force is increased from 0 to F, where the block slides slightly, okay, then up to F, uh, there will be deformation of spring, because this block will not move and it will provide an opposite resistance. Okay, okay. So uh, up to F, it will be the opposite force will be for the acceleration x k2. Okay. Now when and this opposite force will be provided by the friction of this block. Okay. Okay. Once it exceeds the limiting friction, then the block will start moving. Okay, in this direction. Okay, so the maximum value of the force beared by the spring will be the frictional force between this block and this. Okay, so answer should be A. Okay, let's see the explanation. The resistance will be offered by the friction force acting on block, which will cause expansion of spring K2 until it reaches limiting friction. Once the limit of friction force in mu Rn is reached, the block will move and the acceleration of K2 will diminish. Okay, so when the block will start moving, the tension will start diminishing. Okay, next, three connected railway coaches A, B, and C of masses MA, MB, and MC, respectively, are being pulled by a locomotive with force F over a horizontal track. The coaches may be assumed to move on frictionless speed with negligible air resistance. The tension in the connector between coaches A and B is option A F, option B F MA divided by on the option it is divided by, okay, MA plus MB plus MC. Okay, option C F MB divided by MA plus MB plus MC, and option D MB F MB plus MC divided by MA plus MB plus MC. Okay. Now, uh, suppose this is the force acting on the uh, wagon or coach A. Okay, coach A. F is the force acting. Now, mass of this A is ma, and suppose A is the acceleration of the whole system, then the inertial force will be in the direction for this wagon ma into A, and for this it will be mb into A, and for this it will be mc into A. Okay. Now, F this F will balance the inertial force of all these wagons or coaches. Okay. So F will be equal to MA plus MA into A plus MB into A plus MC into A. Okay. So F is equal to MA plus MB plus MC is equal to A. Okay. So F by A is equal to MA plus MB plus MC. Okay. Okay. Now consider the equilibrium of the connector between A and B. Okay. Of the connector A and B. Now forces acting, let T be the tension in the connector. Okay. And then this force in this direction, force in this direction is F. F is this and MA into A. That will be in this direction. Okay. So F minus MA into A. Okay. Will be the force acting in positive x direction, and T is the tension. Okay. So T is equal to F minus MA into A. So now if we put the value of A from here, okay, then it will be MA divided by summation of this. Okay. So now take common as F. Okay. So MA plus MB plus MC minus MA is equal to this. So MB plus MC, F MA plus MB plus MC. Option B is the right answer. Okay. Next, for the beam column configuration shown in figure, the minimum inward buckling load is obtained for the case. Okay, the four different cases are given. The Young's modulus and second moment of inertia are as indicated in the figure. Okay, these are the four different cases. Okay, here L is length. Okay, EI is its moment of inertia. Okay, and here it is E at 0.2i, and here it is EI, and here it is EI, and left here is 0.7, and here it is 0.51. Okay, so this is the case of this is the this is the case of pin joint length. Here it is pin joint length. Here it is the moment of inertia is I, and Young's modulus is P. Okay, so this is the case of pin jointed. Okay, so for pin jointed, we know that the inverse buckling load is P is equal to pi square EI by L square. Okay, for so this is the for this the inverse load is pi square EI by L square, and the condition one is same with extra constant, that is spring. Okay, so the buckling load will be more than, because in this case, because it is providing extra content. Okay, content. Okay, so this is the, so one will be having more load than four, more buckling load than four. Okay, now the second condition is of free end at one end and free at another. Okay, for this the inverse load is pi square E by 4 L square, where L is, sorry, for this, uh, by L square, where L is 0.7 L and I is 2I. Okay, so it comes out as 1.02 pi square EI L square. Okay, so this is also the case of free L. Okay, so here L is 0.51 L and EI is EI. Okay, so by putting this we get 0.96 pi square EI by L square. This is free L. So this is also free L. Okay, okay. So answer minimum load will be according to 4. Okay, that is 5 k by E. Minimum load will be according to sorry, minimum load will be according to 3. Okay, so that is this value. Okay, so answer is 3. So answer is your C answer. Next, a disk of mass 0.25 gram and radius r is equal to 10 mm is at rest relative to massless horizontal turntable spinning about a vertical axis at a at an angular speed of omega 2 radian per second. The turntable is assumed to be mounted on frictionless bearing. Another identical initially non-rotating disk is dropped onto the spinning disk. Friction causes both disks and the turntable to eventually rotate at same angular speed. The eventual angular speed of the disk is option A 0.5 radian per second, option B 1 radian per second, option C 2 radian per second, option D 4 radian per second. So here the one disk is causing rotation of other. Okay, so the initial momentum should be equal to final momentum. Okay, so initial momentum should be equal to final momentum, and initial momentum let first disk is represented by 1. Okay, and second is 2. So the initial momentum of the disk is I1 into omega 1. Okay, now and finally the both start rotating, and suppose the angular velocity is omega 2, then final momentum is I1 plus I2 into omega 2. Okay, so I1 is equal to mr1 square by 2. Okay, for this one, and for this two it is m2 r 1 square by 2 because both are having the same radius. Okay, so m1 r1 square omega 1 divided by 2 m1 plus m2 r1 square by 2 into omega 2. Okay, now putting the value m1 is 0.25. Okay, and a disk of mass and other identical disk. So M2 is also 0.25. So M1 plus M2 will be zero point 0.5, and R1 is 10 for both. Okay, because identical so will be defined omega 2. That is 1 radian per second. Okay. Next, a rocket in the atmosphere is accelerating upward with acceleration a meter per second speed. The natural frequency of a spring mass system bracket with mass m kg and spring constant k newton per meter suspended vertically inside the rocket is okay. Options are given, and G is the acceleration due to gravity. Okay. Option A k bar by m. Okay, where k bar is less than 12. Okay. B root k by m. C mg by ma. Sorry, kg mg by ma. Okay. Sorry, g. mg by m, that is not the question. The k by m 1 minus a by g. Okay. The natural frequency does not depend upon the is k by m. Okay. Natural frequency does not depend upon the g and a. Okay. It depends upon the k and m only. Okay. So answer is k by m. So our answer is B. Next, an irregular planar body in space is acted upon by a force F 2I plus j at position R1 bracket I plus 2j m m is in meter, okay, and a momentum m vector 3 kilonewton meter at a position R2 is equal to minus 2I meter, okay. The corresponding equivalent force F naught and moment m naught at the origin are a f naught vector is equal to 2I plus j newton m naught 3k plus 3k newton meter b f naught vector 2I plus j newton m naught 0 newton meter c f naught vector minus 2I minus j newton m naught minus 6k newton meter d f naught 2I plus j newton m naught 6 k newton meter. Okay. So here it is given that the force is this. Okay. And that is acting at this at R1. Okay. Now let this is the given force. That is F is equal to 2I j and this is the vector at which it is acting. It is R is I plus 2j. Okay. Now apply a opposite, equal and opposite force at origin. Okay. Now this F and this F will create a moment. Okay, and this F will be the force transfer. So at origin, the force transferred will be transmitted will be in the same direction as that of F. So F is 2I plus J. Okay. Now the moment transfer will be given by R1 into F. So this is R1. R1 is I plus 2J and F is 2I plus J. Okay. So by the vector product we get the moment transmitted due to F is minus 3K. So and the moment acting on the at any point at distance will be transferred as same as that of that. Okay. That is actual value. So at a distance it is minus 3 and due to m 3 kilonewton meter, sorry 3k newton meter. Okay. So the total other moment is also given. So this is the moment. Okay, 3k newton meter. Okay. And from product of this we are getting minus 3k. So the moment will be 0 and force will be 2I plus j. So answer will be 2I plus j, moment will be 0. Okay. So because this moment is in uh, this moment is in anti-clockwise. Okay. So it is minus 3 and this moment is positive. Okay. So this is next, a hollow shaft and a solid shaft constructed of same material have same length and same outer radius r. Okay. The inner radius of the hollow shaft is 0.6 r. Assuming that both shafts are subjected to same torque, the ratio of minimum shear stress in the hollow shaft to that in the solid shaft is option A 1.1, B 1.2, option C 1.15, option D 0.94. Okay, so hollow shaft is given. Hollow shaft and metal, hollow shaft and solid shaft are given, and metal is same, and the length is same. Okay, and the outer radius is same. Okay, the inner radius of the hollow shaft is 0.6 meters. Okay, now you have to calculate the shear stress in the hollow shaft, the ratio of the shear stress in the hollow shaft to that hollow shaft. Okay, now take initially the hollow shaft and use torsion equation. So TH by GH is equal to tau H by R. Okay, so we can find out stress in uh, and H and GH will be uh, outer D4 minus inner D4. Okay, so the stress will be this 32 by into pH by 30 13.9. Okay, and for the solar shaft it is by 32 pH R4 by 16. Okay, so this is the so as the metal is same. Okay, and the applied torque is also same. Okay, so tau H will be equal to tau C. So the ratio of the shear stress is 15 by this. Okay, ratio of these two. So answer is 1.15 option C. Okay, question. Okay, option C 1.15. Next question. A point in a beam experiences a tensile stress due to bending of 50 Newton per mm square and a shear stress of 20 Newton per mm square. The principal stress is option A 17 Newton per mm square tension, B sorry 67 Newton per mm square compression, B 00 T 57 Newton per mm square tension, 7 Newton per mm square compression, D 52 Newton per mm square compression and 15 Newton per mm square tension. So this is a direct formula based question. So sigma x is 50 and sigma y is 0. Okay, and tau is 20. So this is the sigma 1 and this is sigma 2. So answer is option C. Okay. Next, question 10 to question 22 carry 2 marks each. Question 10. Consider a simply supported beam loaded either by a uniformly distributed transverse load or by a concentrated transfer load applied at the center such that the maximum bending stress in both cases is same. The ratio of strain energy for the two cases is A 4 by 5, B 5 by 8, C 8 by 5, D 1. Okay. So this is simply supported beam and W is the UDL. Okay. So for small w is the UDL. So RA will be WL by 2 and RB will be WL by 2. Okay. So maximum bending moment will be WL square by 8. Okay. That is formula. Okay. That we can write. Okay. Now using bending equation M by I, sigma by y, M is so sigma is WL square by 8, by sigma is WL square by 8 into 64 by I. Okay. I is pi by 64 d4. Okay. And pi is equal to so sigma is coming out this. Okay. Now when the point load is applied, okay, the bending moment will be W by 2 into L by 2 W by 4. Okay. Now again using the same formula M by I into Y, we have this. Okay. Now in the ratio of as the bending stress is same in both the cases, so we can create these two. Okay. And from this we have W is equal to W by 2. Okay. Now you have to calculate the maximum bending energy. Maximum bending energy is nothing but only a strain energy. Okay. Only a strain energy. Okay. So the strain energy is given as uh, in the first case, strain energy is m in both cases is m square dx by 2e. So here m is w, sorry r w is by 2 into x. Okay, w is by 2 into x minus wx square by 2. Okay. This is due to RA, this is due to UDL. Okay, so putting the limit L 0. Okay, so W square 8EI or 0 to N. Okay, so W square by 8EI. Okay, LX minus X square. Okay, putting a limit. So integrating them. Okay, so we can have uh, this as W square L5 30A 32 88. Okay, in the second case, only UDL is given. Oh, sorry, only central node is given. So bending moment is W by 2 into X. Okay, what is the value 0 to 12 by 2? Okay, so here integrating them. Okay, and putting W is equal to small w by 2 that we have derived. Okay, we have derived uh, that we have derived. Yes, okay, so and then we can find out that U2S W square L5 8 by 48 EI. Now the ratio of these two will be ratio of this U1 and U2 will be 48 by 30, that is 8 by 5. So answer is C. Okay. Next, a small railway bridge. A small railway bridge is connected from identical steel truss member, each of length L, cross-sectional area A, and Young's modulus 3. A train stops on the bridge. Okay, the load applied by the train on the truss on one side of the bridge may be assumed to act at pins A, B, and C as shown. The displacement of support C due to this loading, option A 0, option B QL by A, option C root 3 QL by 4 AE, option D QL by root 3A. Okay. So when the here it is given that when the train stop on this bridge, a point load is acting on this, a point load is acting on this, and a point load is acting on C. Okay. Now it is asked that what is the displacement of the C. Okay. So as there is only vertical load and there is vertical support at C also. Okay. So there will be no deflection of C. Okay. The whatever deflection will try to occur will be balanced by this support. Okay. So answer will be 0. Okay. Next, a vertical pole cantilevered at the bottom has solid cross section of diameter D 49.21 mm. It is loaded by a horizontal force P 6675 Newton at the top, and the maximum shear stress in the pole is A 4.25 Newton per mm square, B 5.68 Newton per mm square, C 4.68 Newton per mm square, D 7.5 Newton per mm square. Okay. So this is the 6675 load acting on the pole on the in vertical at a at a length L. Okay, pole is L. Okay. Now the average shear stress, if we do not consider the bending. Okay, then the average shear stress will be into this area. Okay, so that load is 6675 Newton for the pole. This okay. Now as length is not given. Okay, so this is the average shear stress. Okay, now and the section is circular section, and in circular section we know that tau max is equal to 4 by 3 tau average. So 4 by 3 into the 3.51. Okay, is equal to 4.68. Option is C is the answer. Okay, next, a striker with mass m 2 kg is attached to the end of a of massless rigid bar of length r 0.3 meter. The bar is held to support A and swings down from an initial horizontal position such that the striker hits mass m 5 kg elastically. Okay. The mass m slides in a straight line. Okay. Slides in a straight line along the table from point B towards the string located at C, 0.2 meter away from B. Assume this is the figure. Okay, this is the mass capital M. Okay, this is small mass M. Okay, 0.3 meter from this, okay, and it also 0.3 meter in height. So that is that mass is 0.2 meter from the spring, okay, and here is this. Okay. Assume that the coefficient of friction in the region BC is UD zero point 0.4. The region CD frictionless. Let the spring constant of the spring be K is equal to 4000 Newton per meter. If the striker rises to maximum height of zero point 0.1 meter below its starting location, okay, uh, the maximum compression of the spring is let acceleration due to gravity g is equal to 10 meter per second square. Dimension of the striker and mass are known. Okay. So it is given that here m is mass and it hits the that mass and go upwards by 0.1 meters. Okay. Maximum height of zero point 0.1 meter. Okay. So the potential energy initially it is according to height of zero point 0.3 meter and according to and finally it is according to zero point 0.1 meter because it rises after striking also. Okay. So the loss in potential energy by the mass m is 2 into 10.3 minus 0.1. Okay. It is given now. If the striker rises to maximum height of zero point 0.5 meter below its starting location. Okay. Below its starting is it should be striking location. Okay, it should be striking location. Okay. So this is the potential energy lost by mass is 4 Newton meter. And K gained by mass is let u is the velocity of the mass m after striking. Then the K will be m number 2 and u square. Then u square is will be 4 into 2 by 5. Okay. So u will be 10 by 5, 1.6. Okay. U square will be 10 by 5, 8 by 5. Okay, it will be 1.6. Okay. So as the now this block has gained kinetic energy. Okay. Now it will start moving in this direction. Okay. And if there is friction in this uh, path, okay, then if there is friction in this path, then the kinetic energy will be lost. Okay, due to friction. Okay, so kinetic energy will be lost due to friction. So this loss in kinetic energy will be equal to the kinetic energy gained by will be the frictional force into the distance traveled. Okay, now the mass of the block is mass of the block is your m is given as sorry m is your 5 kg. Okay, so rn is also 5. Okay, and 5 into g. Okay, and friction force will be mu rn that is 20 newton. Okay, now the this force into distance traveled by the mass is the energy. Okay, so that is 20 into 0.2 that is 4 newton meters. Okay, so this uh, gain in sorry this loss in energy due to friction will be equal to the will be equal to 4 newton meters. But here the energy initially the mass is having that is 4 newton meters. Okay, so here the energy of the mass is 4 newton meter and the here the energy lost is 4 newton meter. So all of the energy is lost from B to this point. Okay, so no energy is left to compress the spring. So the compression of the spring will be zero. Okay, so answer will be A. Okay, answer will be this is A answer. Next, A cube made of aluminum of dimension zero point 0.1 meter into zero point 0.1 meter into zero point 0.1 meter rest against a rigid wall with normal in y direction. Okay, as shown in the figure. Another rigid wall is located at a clearance of zero point 0.2 meter, 2.2 mm from the block. Assuming all contacts to be frictionless, if the block is heated by del T is equal to 150 degree Celsius. Okay, the normal stress sigma yy induced in the block is for the aluminum E is equal to 70 GP and mu is equal to zero point 0.3 alpha is equal to 20 to 10 to the power minus 6 per liter. Okay, here the the options are sigma yy minus 7 MPa, sigma yy plus 7 MPa, sigma yy minus 7 MPa, sigma yy. Okay. Here the clearance is given, okay, and the increase in temperature is given, that is 150 degrees Celsius. Okay. When the temperature is increased, the new block will expand. Okay. So, but according to 150 degrees Celsius, the expansion is 0.003, okay, or 0.0, but the clearance is given as 0.2 mm. Okay. So the aluminum block cannot expand freely up to 0.3 mm. So this expansion will be restricted, okay, by this wall. Okay. So the expansion restricted is 0.3 minus 0.2 is equal to 0.1, okay, mm. So corresponding to this 0.1 mm, there will be stress in the aluminum. Okay, so that is expansion restricted by length into E. Okay, that is strain O into E. Okay, so answer is 70 MPa or compressive stress due to restriction of expansion is because the expansion is being restricted. Okay, there will be compressive stress. So answer will be minus 70 MPa. So answer is option C. Okay, next. A thin-walled spherical vessel made of a linear elastic isotropic material has inner radius r and thickness t before pressurization. When subjected to internal pressure P, element of pressure vessel wall experience a state of stress described by a single point sigma tau, okay, is equal to PR by 2t 0. Okay. In the Mohr circle, the reduction of wall thickness due to pressurization, A increases with it, B is independent of it, T decreases with it, depends upon the elastic proportion. Okay. So here it is given that the sigma is given as PR by 2. Okay. And other stress shear stress is 0. Okay. So and vessel is spherical vessel. Okay. So the shear stress is 0. Okay. So the that sigma is this PR by 2t. Okay. So strain in the thickness or decrease in thickness will be sigma theta by E into T. So T will cancel out. Okay. So as thickness is wall is very small and thin pressure in thin spherical vessel, so there is no differentiation between outer radius and outer radius. So it doesn't depend upon T. Okay. So it will depend on elastic properties, that is E. Okay. So answer should be D. Okay. Next, for small oscillation, the natural frequency of the system in terms of K, A, B, and M is assuming ideal joints and massless rigid load ABC. Okay. So we have to find out the natural frequency of the system. K is a stiffness, A is a distance from B, and B is a distance from M. Okay. So when we rotate this or displace this about the fulcrum, okay, then this displacement is theta, and this is theta. Okay. So uh, Suppose I is the moment of inertia of this road, and okay, sorry, as the mass of the this road is zero, okay, so moment of inertia of this road is zero. Okay, now M mass is attached here, okay, M mass is attached here, and it will create a moment of inertia about B, okay, about B. So the moment of inertia about B will be M into B square into theta double dot, okay, and here it should be uh, when when this A B C is given a small displacement theta, so then this road will compress, okay, so there will be downward force K theta, okay, and moment of inertia mb square theta double dot, okay. So now taking moment about the I theta double dot, I theta double dot plus K A theta into A, okay. So I theta double dot is plus K A square theta is equal to 0, okay. So omega n is your K A square divided by mb square, okay. So answer is your option D, K A square by mb square D, okay. Next, common data question for 17 and 18. A steel cylindrical pressure vessel has an inner radius of 1.8 meter and a wall thickness of 20 mm. Okay. Question number 17. For an internal pressure of 800 kPa, the maximum shear stress for cylindrical part of vessel is A 16 MPa, B 18 MPa, C 20 MPa, D 0. Okay. Okay. At which of the following internal pressure will the cylindrical vessel yield as per the Pascal criteria if the yield stress of the material is essentially 320 MPa. Okay. So here the internal pressure is 800 kPa. Okay. As radial stress is not given, or nothing is given about radial direction. Okay. So we will assume the hook stress as maximum stress. Okay. And uh, longitudinal stress as linear stress. So hook stress is PD by 40 and longitudinal stress is PD by 40. So tau is PD by sigma theta minus sigma L by 2. So it is PD by 80. Okay. So P is 800 kPa and D is your 1.8 into 2. Okay. Diameter and T is 20. Okay. Now shear stress is PD by 80. So we can put the values in here. Answer will be D. Next, according to Tresca criteria, uh, we have to find out tension. Okay. Now the maximum shear stress we have found out that is 18 MPa. Okay. Okay. And this is sorry the shear yield sorry given that the normal yield stress is 320 MPa. Okay. And so shear yield stress will be according to pressure area will be 320 minus by 2, right? It will be 160 MPa. Now it is PD by T that we have found as maximum. The shear stress is PD by 80. Okay. So by putting this equal to 160 PD by 80, P will be 701 MPa. Option is B. Question 80. Sorry, 701. Option B. Okay. Next, common data for question 19 and 20. A steel beam of rectangular cross section 25 mm wide and 75 mm deep is pinned to supports at points A and B, where support B is on roller. Okay, this is the two sports. These are the two sports. Okay, this is roller sport. This is simple sport. Okay, The Young's modulus of steel may be assumed as 2.2 into 10 to the 5 Newton per unit square. Okay. The ends of the beam are loaded with 5 kilonewton. These are the two ends loaded with 5 kilonewton. The maximum bending stress in the beam is option A 0, option B 64 MPa, option C 128 MPa, option D 32 MPa. The vertical reflection of the ends is 4.92 MPa, 4.58 MPa, C 9.3 MPa, and 9.8 MPa. So input all are the so these are different all are the okay. Now this is our hanging beam. Okay. Now to find out the maximum bending stress, we have to find out the point of maximum moment. Okay. So these are the reaction because they are at equal distance R and RB. Okay, so the reaction will be 5 and 5. Okay. So if we draw the shear core diagram, then it is 5 down and 5 up. No shear stress here and 5 up and then 5 down. So there will be no shear stress between A and B. So as shear for the zero between A and B, so the bending moment will be maximum. So the M max is 5 into 0.3, 5 into 0.3, so that distance 0.3, 1.5 kilonewton meter. Okay. So using bending equation M by I is equal to sigma by Y, M is equal to 1.5, M is equal to 1.5 kilonewton, 1.5 into 1000, okay. And I is 25 into 75 cube by 12. I is equal to your dimensions of the local given, that is 25 and 75, okay. So 25 into 75 by 12 and your y is 75 by 2. So sigma is your 64 LP. Option B is the right answer for question number 19. Now, if we want to calculate the reflection, we use the strain energy method or particle law method. Okay, the strain energy is given as uh, 0 to for portion CA. This portion here. So this portion is your CA. Okay, for this portion it is T Px by 2 EI. Because movement is this, okay. So this is the strain energy in this portion, okay. And for portion AB, it will be movement is constant, that is 0.2.3, okay. So strain energy will be this according to this. Exhibit by 0.3, okay. Now the portion, the strain energy of the portion CA and portion BD will be same because they are subjected to identical loads. So this portion and this portion will be having same strain energy, and for this portion the strain energy will be according to this, okay. Okay, the total strain energy will be this, okay. Okay, now deflection under load P. To find out deflection under load P, where we have to differentiate value by P. So if we differentiate them, okay, here it should be 2P, 2P. Putting the value of P, okay, we can get 4.3. The nearest option is 4.5. B answer. Next, statement for linked answer question 21 and 22. A cantilever beam of unknown material which is homogeneous, linearly elastic and isotropic and an unknown cross section which is uniform and symmetric is given in the figure. The thickness of the end string is K is equal to 2000 Newton per meter and free load P is equal to 1000 Newton. The length of the beam L is equal to 1 meter. Okay. So this is the EI, sorry, the Young model velocity E and movement velocity I. Okay, so this load is here. So that P may be acting and M may be acting. Okay, there are two questions based on this statement. But if the deflection at the free end under load P with and moment 0, M is 0, okay, is measured as delta is equal to 5 mm and the flexure unity EI over the beam is in Newton meter square. Okay, A 6666. Okay, B 66 triple zero, C 67300, D 64000. Next question, the value of the resistance. Sorry, first of all, we will solve this question. Okay. Here the P load is being applied and M is zero. Okay. And this expansion of the this before deflection of the this beam will be resisted by the spring. Okay. So R is the uh, reaction by the spring. So this R will be reaction by spring and R will be acting this. Okay. So the net load that is used to deflect this beam will be P minus R, because this R is used for extension. Okay. So net load will be, this R used for extension, net load will be P minus R. Okay. So net force is P minus R. Okay. And we can use the formula for cantilever with point load at, for cantilever with point load at end point, that is WLP by 3I. So that is P minus R LP by 3I. Okay. Delta is equal to delta. Okay. Now R is your K delta. K is your stiffness and deflection of the spring is given as 5 mm. Okay. So we can have the R as 200 to 5. Okay, this. Okay. Okay. Now putting this value delta as 5, because expansion is equal to that deflection. Okay. Putting that value as to 5 and P is equal to 1000, we can have R is equal to EI is equal to 66 0.0 Newton meter square. Okay, next. Now it is given that the point end moment is also acting. Okay. Now it is given that the value of additional end moment M in Newton meter required to obtain upward deflection of 1 mm at 3 m is moment is positive in counterclockwise direction. Okay. So this moment is positive. Okay. And now due to load P, the deflection is 5 mm. Okay. Now it is asked that the upward deflection is 1 mm. Okay. Now, now this M will create a deflection, uh, 1 minus 4, 5 mm, that is minus 4 mm. Okay. Upward deflection will create, sorry, upward force will create 5 mm, and moment is net is 1. So the deflection created by this moment will be minus 1. Okay. So when P is upward direction, as in previous case. Okay. Okay. So the previous deflection was 5. Okay. Now to obtain net deflection 1 mm deflection. Okay. The deflection produced by M should be minus 4 mm, because 1 minus 5 is 4. Okay. So using Macaulay's method, now the deflection due to M is minus 4 mm. So using Macaulay's method, EI is equal to DI is d square y by dx is equal to M. So d square y dx is equal to M by EI. Okay. So dy by dx mx by EI plus C1. Okay. Differentiating. Okay. Differentiating again, y is equal to mx square by 2EI plus C1x plus C2. So x is 0. Here we have taken this. Okay. And this. Okay. When x is 0, deflection is 0. Okay. When x is 0, dy by dx is 0. Okay. So this is 0. So the y is mx square by 2a, putting the value of x, that is 1 meter. So and y as 4 minus 4 mm. We can have m as minus and ei as 66000. We can have my m is as minus 8 Newton meter. So option C is the correct answer. This is the option C. Okay. Thank you.